Hi, this is Justin, and in this video I'm going to be going over a little bit about the sensors we'll be using in the flow calibration lab, and then a little bit about how uncertainty is calculated, how you perform a direct comparison calibration, and some of the things we'll be looking for this lab report. So the first thing I'm going to do is talk a little bit about the three sensors we'll be using. So there is a rotometer, there is a vortex shedding meter, and there is a magnetic inductance meter. So the rotometer is a completely analog gauge. It works based on balancing a drag force with some sort of restoring force. And in our case, it is a spring and a weight. So there is a bobber that's in the flow path, and it's got a spring behind it. So as water flows over that bobber, drag is created, and that tries to push it up in the column. The weight of the bobber, with gravity affecting it, and the spring try to push it back down. So it is marked, and the column that it's in is graduated. So using the line on the bobber, the flow rate can be directly read off of the graduation marks in the column. So it's an analog display that you read the flow directly off of, and we're going to be reading it in gallons per minute. We'll be doing all of these sensors in gallons per minute. And these do not require any power. They operate simply based on the water flowing through them, but that means that there's no easy way to do any sort of data acquisition on these kinds of sensors. You have to have a person go physically look at it to know what the flow is. So the vortex shedding meter. So there is a body in the flow path. As water flows over that, vortices are created. So those vortices are then carried downstream in the water flow. So vortices are created, they get carried downstream. So the vortices are moving at whatever the speed of the flow is. So our sensor uses a piezoelectric element, but any sort of ability of sensing these vortices passing works. So you have some sort of sensing element downstream from that bluff body. So you can correlate the speed that those vortices move past that sensing element to the flow rate. Because we know that the vortices are moving at the speed that the water is flowing, so if we know the area of our sensor, we can find what the actual flow rate is. So these require power, so they are slightly more complicated to operate in that you have to wire them up. But that also means that they have some sort of electrical output that makes data acquisition a lot easier. So you can remotely sense with these. You can hook them up to a computer or some other sort of data acquisition system, and you can keep either a log or you can have a direct readout or both of what the flow is. So the magnetic inductance meter is going to be the calibration standard. So for this lab, we will be calibrating the rotometer and the vortex shedding meter through direct comparison with the magnetic inductance meter. So that means we are saying the magnetic inductance meter is measuring the actual flow, so whatever the real value for the flow rate is. And we're going to do a calibration to try to make the rotometer and the vortex shedding meter read the same as the magnetic inductance meter. So the magnetic inductance meter works on something called the Lorentz force. So that is a force vector is equal to a charge times some velocity vector crossed with a magnetic field vector. So charges are present in the water because there are ions in it. So there are positive and negatively charged particles in there. They're in the water, so they're moving with some velocity in a known direction, that is the water flow. So the sensor is applying a magnetic field. This magnetic field, combined with the velocity and our charges, creates a force on those charged particles. So positively charged particles get a force in one direction, negatively charged particles would get a force in the other direction. So this creates a potential difference. That would exist across the sensor. So this potential difference is going to be related to how separated the charges get, so how many of the charges get moved to one side and the other side. And that's going to be directly related to the force. And that force is directly related to the velocity here. It's directly proportional to whatever the velocity of those charged particles is. So the particles are moving at the speed that the water is flowing. So that means we can correlate the potential difference that's measured with the velocity. And that's how the magnetic meter works. So this again requires power, but that also means that output is typically easier to measure and much easier to acquire digitally or record in some way than it would be, say, for the rotometer. So these are the three sensors that we're using in the lab. Again, we'll be calibrating the rotometer and the vortex shedding meter using the magnetic inductance meter as the standard. So how do we perform the actual calibration? So the overall calibration equation, which I'm going to call FCal, is AX plus B, which is our actual calibration part, and then an uncertainty analysis. So del A, del B, and del standard. So del A is called the scale uncertainty. Del B is the offset uncertainty. And del standard is the uncertainty of the sensor used as a standard in the calibration. So for both of the calibration equations you make, you'll have one for the rotometer and one for the vortex shedding meter. Del standard is going to be the uncertainty of the magnetic inductance meter. It is always the uncertainty of the sensor you used as a standard in the calibration. So this will be our actual how we perform the direct calibration part, and then this will be the uncertainty analysis. So how do we find this calibration? So you're going to have two plots, one for each sensor being calibrated. You'll plot the standard flow on your y-axis, so this will be the output of the magnetic meter on the y-axis. And you will plot whatever sensor you're trying to calibrate as your x values. So you will apply a linear fit to this data, and that will give you an equation y equals ax plus b. So your x's are your uncalibrated data points. Your y's are your standard values. And this gives you your A and your B for your calibration. So we'll call that fcal of xi. So you would plug in each of your uncalibrated data points into this, and that would give you the calibrated values for that sensor. And the idea is we want them to be exactly what the magnetic meter read at those data points, but depending on how the calibration actually goes, they usually won't be exactly what the standard was. The idea is we want to force our uncalibrated data points to be closer to what the standard was measuring at that same point. So then you've got to do an uncertainty analysis. So you've got to calculate these del A and del B. So del A, again, is the scale uncertainty, and it's called that because it's being multiplied whatever your readings are. So it increases as your actual measured values get larger. And del B is your offset uncertainty. So del A is plus or minus a t value that you'll get from a table in the appendix, and that will be based on a 95% confidence interval. You'll have a standard deviation SYX, and I'll give you the equation for that in just a second. And then you'll have another standard deviation SXX. So that's for the scale uncertainty, del A. Del B is plus or minus that same t value, SYX, and then the square root of 1 over n plus x bar squared over SXX squared. So n is the number of data points, SXX is another standard deviation, x bar is the average of your uncalibrated data points for that sensor. So SXX, and note that I'm giving that to you as a square, is the sum of your individual data points, xi, minus your average of your uncalibrated data, squared. Oh, it's the sum of this quantity. Your SYX, and again, giving that to you squared, So this is your standard, what it read at that data point. This is your calibrated for values for the sensor you're trying to calibrate. And again, n is the number of data points. So your SXX value is looking at how spread out your data is. So for the same number of data points, if all of those data points are close together, your uncertainty will be smaller than if you took those data points over a larger range. So this is really looking at how close all of your data points are to each other. Here we're looking at how close your calibrated numbers came to what the standard was reading. So what we want for a low uncertainty is numbers that are close together and that come very close to what the standard read. So those are the two things that will give you a low uncertainty. Is a good calibration as far as your calibrated values were very close to what the standard was, and the data points aren't very spread out. So again, you'll have one of these for the rotometer, and you will have one of them for the vortex shedding meter. So A, B, del A, and del B will all be different between the rotometer and the vortex shedding meter. Del standard will be the same because it's just the uncertainty of the magnetic meter, because that's what we used as the standard. So there is an example in Appendix A going through this, if you have any trouble with it. So the last thing I'm going to be talking about is comparing the uncertainty that you find to what the manufacturer said it should be. So this is how we determine if a calibration is any good or not. So every sensor will have an uncertainty given by the manufacturer, and that is a uncertainty value where if it is well calibrated, your uncertainty should be less than that number. So one thing I want to talk about is that uncertainty is not error. Uncertainty and error are not related to each other. They are very different things. So as an example, if you had a stick and you wanted to know how long that stick was, you could have one person look at it and say, I think that stick is about 6.5 inches. You could have another person use a ruler, measure the stick 30 times, average all of those measurements together, and say the stick is 6.51 inches. Well, if the stick is actually 6.5 inches, you had no error in your guess, but you had a lot of uncertainty in that guess. Whereas the person who measured it 30 times had a little bit of error, but they had almost no uncertainty, or very little uncertainty in that measurement. So uncertainty is how confident you are in a measurement. So if you just guess a value, you have a lot of uncertainty. It could be right, but it could be very, very far off. If you have a low uncertainty, it means you don't know what the error is. You could be off, but the chances are if you are off, you're off by a small amount, and you know that within a certain confidence, you're close to what the actual number is. So you always want to have a low uncertainty in measurements, because that gives you confidence to say, okay, this is a good number that I'm getting out of this sensor. Whereas with a large uncertainty, you don't know if you're getting a good number or not. So we want you to compare the manufacturer uncertainty to your calculated uncertainty. And we want you to compare like numbers as well. So comparing the same values. Okay, so for the rotometer, as an example, so the manufacturer claims that the uncertainty of the rotometer should be less than 5% of the full scale for that sensor. So that is 5% of 10 gallons per minute. Because 10 gallons per minute is the maximum flow that the rotometer can measure. So you want to compare that with your del A value for the rotometer times your max flow that you measured and plus del B. So you'll have your scale uncertainty multiplied by the max flow that the rotometer measured plus your offset uncertainty for the rotometer. So this will be a number in gallons per minute. This will be a number in gallons per minute. So that is something, that's what I mean by comparing like numbers. So don't say 5% and try to compare it to some number over here. Don't give me just del A or del B and try to compare it to a number in gallons per minute, because neither of those are making sense as far as, if you're just looking at del B, you aren't looking at all the uncertainty, and you don't want to compare a percent to a number in gallons per minute because those don't mean anything compared to each other. So again, this is for the rotometer. So the vortex shedding meter has a different manufacturer uncertainty. You will have different del A and del B values, and the vortex meter will have a different max flow that it measured. So again, this is just the max flow that sensor read. That was the largest reading you got from that sensor. So for the rotometer, it's going to be 8 gallons per minute. For the vortex shedding meter, it will not be 8 gallons per minute. So this is what we're looking for when we talk about comparing uncertainties. And what we want is your calculated uncertainty to be less than what the manufacturer claimed. Because we didn't use the full scale for any of these, so we should be under that. If it ends up being equal to it, that's okay. But you want this to be less. If it's not less, then we probably don't have a good calibration, and you probably don't want to use that sensor as a measurement device, because you can't really trust its calibration, again, because the uncertainty is high. So you don't have good confidence in the numbers coming out of that sensor. Okay, so we have provided a PowerPoint. There is the manual for this particular lab. And then in the appendix, there is an example going through calculating your del A, your del B numbers, your standard deviations. If you have any questions, go through those first. If you're still having trouble, email one of the TAs and let us know, and we'll try to help you. So again, this will be a report. So make sure you're following the format on there. Try to think about things you lost points for in the granular flow report and not make those same mistakes again. So formatting issues, again, using past tense only, making sure your figures have axis labels. Make sure you're putting units on them this time because your plots will have units. They won't be dimensionless like they were in the first lab. Make sure they have titles. Make sure you give R squared values with your fits. But yeah, if you don't have any problems, good luck, and otherwise, I will see you next time.